the morning session in quantum metrology and sensing. And I'm very proud to announce we have our keynote speaker, Ulrik Andersen from DTU today.
Thank you so much. This is working. So thank you so much for the kind invitation. It's my first time in Bristol, and I really enjoyed the workshop so far. So I'm here to talk about some of our work on continuous variable quantum sensing. So the group there's a photo of the group here, and we do a different type of research. And this is mainly funded by the Danish National Research Foundation, DNRF, and in terms of a center that we call Center for Microscopic Quantum State. It started last year, and it runs for 6 + 4 years. We also have support from numerous other foundations, private foundations and public foundations, but also from the flagship. So we are affiliated with 2 quantum communication projects in the flagship, one which is dedicated to making quantum devices smaller and cheaper. This is the Unicorn project, and one which is devoted to developing a continuous variable quantum key distribution, which is the Civic project. But in our group, in addition to doing continuous variable quantum information, computation and communication and sensing, we also do diamond quantum technology. So we have experiments where we are using color centers in diamond to sense magnetic fields with extremely high sensitivity. And right now we're using them to sense magnetic fields from biological samples, like muscles from mice, and also from brains of mice. So we also have projects where we're trying to extract the single photons very efficiently from color centers, nitrogen vacancy centers and germanium vacancy centers from diamond or in diamond placed inside a micro cavity. So this is work that I'm not going to talk about today, but a PhD student in the group, Rasmus, is also here, and he has a poster presentation about this project. So please meet him later today if you want to learn more about that experiment. We also do some experiments on outright quantum optomechanics. We're not really deep in the quantum regime yet, but we do have some optomechanical experiments, and the goal is to go deep into the quantum regime, making non-Gaussian states of mechanics is like the ultimate goal of that project. And then finally, and not least, we do a lot of work in continuous variable quantum information, and that's what I'm going to talk about today, or part of that work. Okay. So let me just start with setting the scene by very briefly go through what is meant by sensing, quantum sensing. So we basically have those 4 or 3 blocks in the laboratory. So it starts with preparing the quantum state, in our case of light, but it could also of a solid state system or atomic system. But in our case, we prepare a certain state, often a pure state, of the optical field. It then goes through some unitary transformation. It undergoes a phase shift, for example, and this phase shift is then coupled to a parameter of the environment. It could be the temperature, the pressure, or the magnetic field, electric field of the environment, and this is then imprinted onto the face of your optical field. And then at the end of the day, of course, we have to learn about what happened, and then we perform a measurement. And this is basically and then we end up with an estimate of this phase shift, and therefore an estimate of the parameter we want to sense of the environment. There are basically 2 different categories. One that is called sensing, where we're trying to sense just a small phase shift around a certain set phase. So this is what we refer to as sensing. And then there's also the other task of estimation, or like an ab initio estimation of a phase, so we can measure directly, or phase measurement within the whole phase space from 0 to 2 pi. So this task is more difficult, and it often requires some adaptive measurement approaches, some feedback measurement approaches. So in my talk, I will be focusing only on sensing. I mean, sensing a small phase shift around a certain set phase. All right, so this is basically the stage, and then you can go on and look at different limits. I mean, what are the ultimate limits in estimating a phase, or estimating a small phase shift? So again, we have the three blocks. We have a state preparation, we have evolution of the phase, and then we have the final measurement. And then we can define some limits. I mean, the standard quantum limit is the limit that we want to beat in order to get into the quantum regime. And this is what we call the standard quantum limit, which is given by 1 over the square root of n, where n is the number of photons in your state, or the mean number of photons of your state. That's the limit that can easily be reached using a coherent state of light. And many different types of detectors. You can use photon counters, you can use intensity detectors or homodyne detectors, then you will reach this standard quantum limit. If you want to beat that limit, then you need to use more sophisticated states or sophisticated detectors. And then ultimately you will reach what is called the Heisenberg limit, not really limit, but it's like a scaling. So it doesn't scale with 1 over the square root of n, but now it scales with 1 over n. So that's of course better than the standard quantum limit, in particular if you have a large number of photons. All right, so when we talk about photonic quantum sensing, then that means breaking that limit and going towards this Heisenberg scaling. This is the definition of quantum sensing for photonic states. But if you're talking about atomic states or sensing with the diamonds, I mean, we are not even able to break that limit. But so we call it this quantum sensing whenever we are getting close to this standard quantum limit or the shot noise limit. Because, I mean, squeezing the spins of a diamond is extremely difficult, or making entanglement in the spins of diamond is quite difficult. So it's extremely difficult to break that limit for solid state sensing. But in the optical regime, we only talk about quantum sensing when we really go beyond that limit. What is the real limit? I mean, the real limit you can find by calculating the Fisher information for that particular state. So we have a certain state in our laboratory, and then we calculate the Fisher information. This is the maximal information that you can extract about the phase. No matter what detectors, you are just optimizing over all possible detectors. And then you get the quantum Fisher information, and this will give you the quantum Kammerau bound, which is the ultimate limit that you can achieve. So for some state, this is the ultimate limit, 1 over n. But for other states, you also have the scaling, but you have a different prefactor. It very much depends on what state you are considering. All right, so then you can characterize this in two different directions. You can talk about discrete variable sensing and continuous variable sensing. And this is basically determined by the detector. Whether you have discrete outcomes in your detector using a photon counter, for example, or whether you have continuous outcomes of your detector using a homodyne detector. So discrete variable sensing has been around for almost 2 decades. And one of the most celebrated states for sensing or quantum sensing over discrete variables is the noon state. This is the state that is shown here, a very difficult and complex state to generate, and is the number of photons in your state. So setting up this highly entangled state here, in particular if n is large, and you want n to be large, otherwise you cannot really sense with very high sensitivity. This is very difficult to produce, but there has been numerous attempts to produce this state. I have one example on the next slide. So then you form your interferometer here with your noon state. You have a relative phase shift of one arm of the interferometer, and then you have your estimator. And the estimator is a projection onto that noon state, which is also difficult to implement experimentally. So you have to realize there's an estimator here, which is not super simple to do. But if you manage to produce that state, if you manage to implement that estimator, then you will get what we call super sensitivity. That means that you get a sensitivity that scales as the Heisenberg scaling. In addition to this super sensitivity, with that state you also see something that we call super resolution. So if you take the mean value of this estimator and plot this as a function of the relative phase shift, then you will of course see oscillation fringes. And these fringes, they oscillate with a frequency that goes with n, the number of photons in your state. So the more photons, the faster oscillations you have. And that is called the super resolution. And that's somehow, for this noon state, this is somehow related to the super sensitivity, but it's not always related. I mean, super sensitivity is not always related to super resolution. You can actually obtain super resolution in the system only using coherent states, photon counters, or coherent state, even with homodyne detectors, you can obtain super resolution. So it's basically a classical phenomenon. but for the null state is somewhat related to supersensitivity. That also means that in many of the experiments of realizing null states, super resolution has been measured and has been used as quantifying the performance of the system. So here's one example. There are numerous examples of generating null states. So it started with two photon null states, 3 photons, 4 photons, I think up to 5 or 6 photon null states. Here's one particular realization from the group of Takeuchi from 2007, where they produced a 4 photon null state and then made the projector in a very probabilistic fashion. So that means that they have to look at the coincidences and they post-selected to realize the projector. And in that case, they saw super resolutions. I mean, they saw 4 fringes with this 4 photon null state. If they're using a 1 photon state or if they're using a coherent state, they'll just see 1 fringe. So they have C4 or they see super resolution. However, they're not beating the quantum limit or the standard quantum limit in this experiment because it's highly probabilistic. Both the preparation of the state as well as the projector were both highly probabilistic, so therefore you cannot beat the standard quantum limit with this approach. Only recently there was an experiment where the standard quantum limit was broken with a null state, with two photons. So here the detection strategy was improved using superconducting nanowires, so the efficiency was higher, and since it's a 2 photon null state, then it's easy to make the projector. So this was only realized recently. I mean, null state sensing beyond the standard quantum limit. It's also important to note that the source here is still a probabilistic source. You never know when you're generating the state, so you still have to wait until you see something and it happens spontaneously. So another way of breaking the standard quantum limit is to go to the continuous variable regime. Here everything is usually deterministic. The source is deterministic as well as the detector is deterministic and highly efficient. And this is what I will be focusing on now for the rest of my talk, is to treat sensing in the continuous variable regime. So exactly the same setup: state preparation, interrogation, and measurement. And the sensitivity we often calculate using this simple relation here. So this is just the ratio between the variance of the estimator and the rate of change of the estimator with respect to the phase. So this is the relation we use to calculate the limits. For example, if you are using coherent states followed by homodyne detection, then you will get the standard quantum limit, which is not a surprise. So the coherent state is here represented in phase space, so it has a certain displacement and excitation along the amplitude quadrature, and then due to the phase shift, it's shift in phase space. So it simply rotates in phase space, and then the estimator here, I actually wrote x, but it actually means p. So we're measuring the p projection, and then if we measure the p projection, then we have an estimate of the phase shift. But of course, we also have a lot of shot noise. So these two blobs here are overlapping, so therefore there's a lot of shot noise, and therefore it can be difficult to estimate the phase shift. But you can do this with this sensitivity 1 over square root of n. So you can also use squeeze states, and this will improve the sensitivity, which is easy to understand just by looking at the phase space diagrams here. So we now have a squeeze state, so this is squeezed in the p direction, so it's a phase squeezed state. And now, due to the squeezing, it is easier to resolve the phase shift upon projection onto the p quadrature. And actually, you can find that you get Heisenberg scaling using this approach. So using just Gaussian states, which you can deterministically produce homodyne detection, which are highly efficient, then you can get Heisenberg scaling 1 over n. However, you only get the Heisenberg scaling if there's a certain ratio between the number of photons in your displacement and the number of photons in your squeezed vacuum state. Only for a certain ratio, actually you almost have the same number of photons in your vacuum state or in your squeezed vacuum state than in your displacement. In that case, you will get Heisenberg scaling. In most practical realizations, the excitation of your coherent state or your squeeze state is quite large. So the displacement in phase space is quite large, much larger than the number of photons in your squeezed vacuum state. And in that limit, you don't have Heisenberg scaling, and this is the limit we often consider in practice. So here we actually have a scaling like 1 over square root of n, like for coherent state, but you have to multiply it by the variance of the squeezing, which is normalized to the short noise level. So if you have squeezing, then this goes below 1, and therefore you will beat the coherent state limit. But you will not get the Heisenberg scaling for this normal approach, a standard practical approach to sensing with squeeze light. All right, and there has been some applications on using squeeze states for sensing because these states are deterministic, practical to produce. You can actually use them in real life to improve the performance of some sensors. And the most prominent example is the detection of gravitational waves. As far as I know, gravitational waves have not yet been detected with squeeze light, but there was a proof of principle experiments like 6, 7, 8 years ago, first in the DTU 600 interferometer and later in LIGO interferometer, demonstrating that using squeeze light you could improve the sensitivity by around 3 dB. And I also know that they're now installing a squeeze light source in LIGO again in the advanced LIGO, and they will probably in the near future be able to use squeezing for detecting gravitational wave events. So this is a real-life application of squeeze light sensing. Another interesting application of squeeze light sensing is from the group of Warwick Bowen from the University of Queensland, where they detected the dynamics of a yeast cell, of a living cell, with squeeze light. It's quantum enhanced microbiology. And this is what is which is shown here. So this is the mean squared displacement as a function of a delay, right? Where you're simply trying to measure the mean squared displacement of a yeast cell, which is trapped in a tweezer. And then using normal coherent state of light, then you get all the blue dots here with standard deviation given by the blue shaded region. Using squeezing, then you can do a little bit better. Then you see the standard deviation is much lower, or not much lower, but it's lower by a factor of 2 or so. So it's a proof of a concept experiment and very neat one, I think. So we have also realized a couple of applications of squeeze light sensing in our laboratory, and I'll go through those 2 applications in the next 2 slides. So the first one is about using squeeze light for enhanced cooling of a mechanical oscillator. So this is a silicon nitride, silica microtoroidal cavity, and this supports optical modes in terms of whispering gallery modes along the circumference of the toroid, and it also supports mechanical vibrational modes. So it's wobbling, and these 2 modes can couple inside the system. And the idea with this experiment was to cool this mechanical wobbling mode, this vibrational mode of the cavity. And this is done by first measuring the motion. That means sensing, and then use this information that you gain. And of course, you want to maximize this information. Use this information to stop the motion using some feedback mechanism. And what we did here is that we did a homodynamic measurement to extract the information about the phase of light, and the mechanical motion was imprinted onto the phase of light. And we used this information to stop the motion using electrodes that were placed around the micro toroid. And that capacitor that we made created like a gradient electric field, and this gradient electric field created a force onto the mechanical oscillator. And then by controlling this force with the measurement outcome here, then we could damp the motion and thereby cooling the system, ideally down to the ground state. But this was done at room temperature and was done at normal pressure, so we couldn't really cool that far down. But it was just like a proof of concept that if you're now improving the sensitivity, that means using squeezing for measuring the motion, then you should be able to improve the cooling factor. And this is what we have shown here. So if you, this is the temperature as a function of the feedback gain. So there's like a gain in this feedback loop here. And the higher the gain, the more you cool onto a certain point, because at one point you cool the signal down to the noise level of your optical field. So that means that you're just using the noise of the optical field to cool, and that gives you the minimum of cooling. That's what you reach here. That's the minimum. And then if you try to cool further, I mean increasing the feedback gain, then you actually start heating the system because you're feeding back the noise of your measurement here of your optical field. So using a coherent state probe, then you reach this limit here, 149 Kelvin, which is not a tremendously low temperature. But nevertheless, if you use squeezing, then you cool down to 130 degree Kelvin. So that was also just a proof of concept that you can actually improve the cooling by using squeezed light. I will come back to later how we actually make the squeezed light source. Along the same vein, we used such a system to detect magnetic fields and improved it using squeezed light. So here, again, we use a microtoroidal cavity, and on top of the toroidal cavity, we place a droplet of terphenol. It's a magnetorestrictive material. So it means that if you apply a magnetic field to your system, then this material will expand. If you apply an oscillating magnetic field, then it will be oscillating this material. And this oscillation will be imprinted onto your mechanical oscillator, and it will be boosted at the eigenfrequency of the mechanical oscillator. So that means that if we impose an oscillating magnetic field, the terphenol will be oscillating, and the entire system will start oscillate. And this we can then measure with our light field in the same way as we did for the cooling experiment. So we have an input light field that goes into the cavity. It feels the motion of the cavity. It comes out, and then we perform a measurement with a homodyne detector. So here is just a schematic of the setup. So here we want to maximize the signal, and we want to minimize the noise. I mean, basically we want to increase the signal to noise ratio. And the signal can be maximized by, for example, choosing the right type of material, magnetically restricted material. And the best magnetically restricted material at room temperature is terphenol. So that it will give the highest expansion for a given magnetic field. So that's the only way of that we can increase the signal. I mean, of course, we can also try to structure the toroid in a different way so that it absorbs the expansion a bit better. Another way of increasing the SNR is to decrease the noise. And how do we decrease the noise? I mean, there are basically two noise sources which are important in this system here: the noise source of the mechanics and the noise of the light field. So there's the thermal noise of the mechanics, and this is a white noise. So you have this at all frequencies, and it's simply triggered by the finite temperature of the environment. So it triggers the photonic motion in all degrees of freedom, and this you cannot get around because we want to do this at room temperature. So there is a lot of noise, thermal noise, due to the finite temperature. And this is amplified at the resonance frequency of the mechanical oscillator. And this is what you see here. So this is the noise power of a mechanical oscillator at 10 megahertz. So we see there's a lot of noise. This is just thermal noise, which is amplified by the eigenfrequency of the mechanical oscillator. But if you go off that frequency, that means if you're off resonant, if you're out here, then this is not thermal noise that you see. Then you cannot measure the thermal noise. But this is simply noise of your laser source. So here, this noise floor here is dictated by the incoming laser noise, whereas the noise around the resonance frequency is basically the thermal noise motion of the mechanical oscillator. And if you're using squeeze light, then the noise floor, of course, will diminish, will go down, and therefore, so you see, we only have around 2 dB of squeezing, which is not fantastic, but this is because it's a quite lossy system. We have to inject our light field, which is not even at at 1550 nanometer is at 1064 nanometer. We inject this into an optical fiber. It goes through the fiber, and then it has to couple into the toroidal cavity, couple out of the cavities. There are a lot of losses involved in this. So we end up with 2 dB of squeezing. And that's actually a source that is producing 13 dB of squeezing that we are using here. So there are a lot of loss on the way. But nevertheless, we see 2 dB improvement in the measurement of resonance. We don't see a 2 dB improvement on resonance. So then you could imagine that you impose a signal onto your resonator. You could impose a signal at 10 megahertz magnetic signal, or you can impose it off resonance. And on resonance, it doesn't matter too much what you're using squeezing because it's already thermal noise dominated. So therefore, using squeezing, you won't gain much in the SNR. But if you do it off resonance, then you will get a lot. You will gain a lot in the SNR by using squeezing. So what the squeezing is doing actually, it helps you sensing off resonance, but doesn't help you on resonance. That means you are simply opening up the bandwidth of your sensor. So you simply use squeeze type to improve the bandwidth of our magnetometer. And here are some measurements. These are the sensitivities of the magnetic field sensor as a function of probe power. And we see there's a small gap between the sensitivity for coherent state, which is this, the red line, and sensitivity for squeeze state, which is blue line. So there's a small improvement in the sensitivity. So that's another application of squeeze light sensing that we have realized and has been published in Optica last year. All right, now I want to look at sensing in a network. So a network, quantum networking is very important in quantum information technology. In quantum communication is of course inherent. I mean, without a network you don't have quantum communication, and we all see that this goes to a global scale these years. But also for quantum computing, you benefit from using a network in terms of distributed quantum computing. But what about sensing in a network? So this has also been treated theoretically. So this list of papers is not exhaustive, but these are just some papers published within the year focusing on sensing in a network or distributed quantum sensing. Do you gain anything about using a quantum network in terms of sensing? I mean, do you gain from using entanglement between different nodes in a network in terms of sensing? That was basically the question that has been posed in many of these papers, and they found that yes, I mean, you can indeed see improved sensing in a network by means of entanglement. So most of those papers have been treating this for discrete variables. I mean, they propose to use GHZ states or twin photon generations to improve sensing in a network. So we want to treat sensing in a network from continuous variables, and we want to use squeezing as we have done in the previous experiments. So again, we have a network of n modes. N nodes, and we want to sense a phase shift in those n nodes. And one way of doing this is to sense the phase shift individually using individual squeezers. So you have squeezer 1 all the way to squeezer n. So you do a phase sensing and a Homerdine detection. Then you have an estimate at every single node, and then you find the average. So the idea is to find the average of all those phases. So to compute the average like this. And that's of course one way of sensing in a network, and you will actually get a nice sensitivity. Of course, you will have the sensitivity for the individual nodes, so it scales with Heisenberg scaling, so 1 over n. Sorry, now I mixed it up. I mean, this should be m is the number of modes, n is the number of photons. Sorry. So n is the number of photons, and here we see Heisenberg scaling. That's what we expect to see for squeezed light sensing, but we don't have Heisenberg scaling in the number of nodes, so m. So this scales with 1 over square root of m. So you have some standard quantum limit for the number of modes using such a network. And I should also mention that the number of photons, n, is a sum of the number of photons in your displacement and the number of photons in your squeezed vacuum state, where r is the squeezing degree. Okay, now we treat a different system where we use one squeeze source and we distribute this to m modes using a beam splitter network. And we know that if you inject squeeze light into a beam splitter network and distribute it equally in this network, then you will get entanglement. So in addition to have squeezing, you also get the multipartite entanglement. And now we propose to use such a scheme for sensing phases at the different nodes. And again, we compute this average phase. And then we calculate the sensitivity, and the sensitivity is now almost the same as for the Sibley case in the number of photons. It still has Heisenberg scaling in the number of photons, but in addition to this, we also have Heisenberg scaling in the number of nodes. So we actually have Heisenberg scaling in the number of nodes. So therefore, using the entanglement network, we gain a square root of n compared to using the Sibley network. And also in the entanglement network, we only use one squeezer, where here we use m squeezers. But of course, here we have to distribute the squeeze source through the network. All right. So, and this is how it scales. So this is the sensitivity gain. So that's the gain in using the entangled network compared to the separable network as a function of the number of modes. And then we simply see it goes up here, scales, is improved by square root of m. And that also depends on the number of photons per mode or node. But this is not realistic, because here I have assumed an efficiency of 1, ideal efficiency, which is of course not realistic in real world. So therefore we have also plotted this for finite efficiencies, and we have restricted ourselves to 4 nodes, because that's what we're going to implement in the laboratory. So here we have 4 nodes, m equal to 4, and now we see the gain is modest. It's not like 30 or 40 or 50 as we saw in the previous plot, but it goes up to 1.6 for an efficiency of 98%. If we have an efficiency of 50%, then we can see it goes dramatically down. But it's also important to know we always have a gain. It's always better to use the entangled approach. We never go below 1 here. So we always benefit from using entanglement. Okay. It's also important that when optimizing this, that it's important that we have the right ratio between the number of photons in our displacement and the number of photons in the squeeze vacuum. And this is what we have tried to plot here. So this is the ratio between the number of photons in the displacement and the squeeze vacuum for different efficiency 1, 95%, and 75%. And we see, for example, if you have very high efficiency, and if you go to a large number of photons per sample, this is the number of photons per sample, so say 1,000, then you see that the ratio between the two is 1/2. That means you need twice as many photons in the displacement than you need in your squeezed vacuum state. That actually requires, this is the squeezing level you require to reach this point here, and then you need 35 dB of squeezing, which is quite a lot. Not realistic. But if you now consider like modest efficiencies of 75%, this is what we realized in the laboratory, then you see the needed squeezing is around 5 dB. So that's doable. Okay, so the experimental scheme, so that's what we will do. So we have one squeeze, and then we split this into 4 nodes in the beam splitter network. We impose a phase shift and homodyne detection, and then we estimate the average phase shift. And this is how it looks like in the laboratory. So we have an optical parametric oscillator. I have another picture of it on the next slide. We produce squeezed vacuum, or displaced squeezed vacuum, because we need displacement also. And then instead of having local oscillator at the 4 individual detectors, we mixing the local oscillator in the very beginning in an orthogonal polarization mode. So we build up a polarization interferometer. So therefore we have the local oscillator in the orthogonal polarization mode. This is just for locking the two. There's a tapping here just for locking the local oscillator in the squeezed vacuum. And then we split this in our beam splitter network with the 3 balanced beam splitters and distribute this to 4 phase shifts. These phase shifts are just imposed using half-wave plates and quarter-wave plates, and then we do the homodyne detection. And we find the average. So this is the squeezing source we are using. So we are using a bow tie-shaped cavity. So we have a strong pump at 800 nanometer. And the nonlinearity of this PPKTP crystal is actually not as high as the manufacturer promised. So that means that we actually need a lot of power in order to reach a reasonable squeezing level. The threshold power of the cavity is 700 milliwatt, and we use 500 milliwatt of pump power in order to produce about 5 dB of squeezing. But then we are producing squeezing at the 1550 nanometer at the telecom wavelength, and this is then sent out of the cavity towards the system. So we impose the displacement in a special way. I'll come back to this in a short while. And this is a squeezing spectrum as a function of frequency. So this is the electronic noise trace. The green trace is the shot noise level, and then the blue trace is the squeezing level. So we have squeezing from around 1 megahertz up to about 10 megahertz. All right. This is just like a small discussion. We also use this squeeze light source for producing a multiplexing source. So the squeezing in such an optical parametric oscillator is actually producing time multiplexed squeezing. So you have like pulses of squeeze state coming out of the source. And the idea of this experiment here was to convert this time multiplexing into space multiplexing. So we simply inserted a switch in our squeeze states. So this is the switch here. It's a fiber switch. And then we're simply switching our squeeze state into 2 different directions. So turning the time multiplexing into space multiplexing. And we did this because we want to produce an EPR state, an Einstein-Podolsky-Rosen state. For this, we need 2 squeezed states. So that means that we now sending the squeeze state into 2 different directions. There's now a delay in time because of the switching. And to catch up with this delay, we injected one of the squeeze states into a long fiber, 200 meters of fiber, and then they were synchronized in time again, and they could interfere to produce EPR entanglement. And we did the full tomography of this 2-mode squeeze state, or this EPR entangled state. And the reason we want to implement this, so this was done all in fiber. I mean, the squeeze state was produced in free space, and then it was injected into fiber. The rest, the switching, the beam splitting, and the homodyne detection were all done in fiber. And the reason that we want to test this switch is that in principle you can keep switching, and then you can produce a lot of squeeze beams just from a single squeeze light source. So it has the capability of scaling up the squeeze light sources. So what is limiting this experiment is actually the efficiency of this switch, which is about 80%. So we lose about 20% of the light in that switch. Okay, so this was just a small excursion. So this was just the measurement result. Okay, so coming back to the squeeze light source for distributed sensing, I briefly mentioned that the displacement was imposed by an electro-optic modulator in the beginning. So we cannot use the displacement of the carrier frequency itself, because at the carrier frequency or at DC frequencies we have a lot of mechanical vibrational noise. So therefore a lot of noise, technical noise, so therefore we could not operate at the carrier frequency. So therefore we imposed a modulation at I think it was 4 megahertz, and then thereby producing a sideband to the carrier, and this sideband is then defining our coherent state or our displacement of the squeezed vacuum state. So you can see this in phase space like this. So this is X and P quadrature in phase space. This is the carrier, and then you have a displacement in, for example, the P quadrature. That's a phase modulation. So therefore, our state is then defined by this small sideband here, and then this is then squeezed, this sideband, and then is rotated in the network. And therefore, by measuring this rotation, we have to perform an X quadrature measurement. So we have to measure along the carrier direction. Okay. So this is again the setup. So we perform measurement at the individual detectors. This is what you see here. This is the spectrum. And we see 0 is the shot noise level. If you go below 0, then you see squeezing, and you see a little bit of squeezing, not too much. I mean, maybe half a dB of squeezing at the individual stations here. So the squeezing in the beginning was split into 4, so therefore you lose a lot of the squeezing. But now if you look at the correlation between the 4, due to the quantum correlation, then you get this one here, and then you see the 5 dB of squeezing. Okay, now we do the phase measurement. So these are time traces at the 4 different homodyne detectors. So what you see here is just the quantum noise. and then you start with 0 phase, and then you change the phase, have one phase change, and then you have a jump. Another phase change, another jump, jump, jump. So this is just the phase changes at the individual detectors. And we see that sometimes you can hardly see the phase change because it's embedded into the noise. But then now you look at the correlation between those four, and then you get a much nicer curve where you can easily distinguish the different phase shifts. Okay, and then we computed based on those measurements here, we computed the mean value as a function of phase, and as well as the variance as a function of phase. And having these measurements, we can compute the sensitivity of our measurement. And this is what we have here, the sensitivity of the distributed network as a function of the number of photons in the network. And here are a couple of lines that are important to note. So the upper one here is the standard quantum limit. That's the limit you will get by using a coherent state. The lower one here, the green one, is the ultimate limit. This is the quantum Kammerer bound. You cannot go beyond that one. And then if you use the separable approach with 4 individual squeezes, then you get to the blue point, or the blue line here. And with the entangled approach, you get to the rate. So we see that we do have an improvement using the entangled approach rather than using the separable approach. And we are also deep in the quantum regime. There's no doubt about this. What I'm plotting here is the photon number ratio between the number of photons in the displacement and number of photons in the squeezed vacuum, both for the separable case and for the entangled case, because it's not the same for the two approaches in order to maximize the sensitivity. We always go for the ratio that maximizes the sensitivity both for the separable case and for the entangled case. And this is now being prepared in a manuscript, and we hope to have this on the archive within the next 2 weeks. Okay, what are then the potential next steps? So first of all, we want to make a much more compact squeeze state source. I mean, of course, we can go all the way down to chip scales, which is very hard, but very important. But there's also this intermediate station where you can try to just make it more compact, the bulk version of the squeezer we have. And that's what we're now trying to do. So right now, the squeezer that we are using for this distributed sensing experiment is a big thing. So first we use a big laser producing like 2 watts of power, and then we use this to produce a lot of frequency doppler light in a frequency doppler in a cavity. And here we produce 1 watt of blue light, of infrared light that is then used to pump the optical parametric oscillator. So it's actually a very big system. So in this new system here, first of all, we're not using a bow-tie cavity, but we're using a very small linear cavity of 1 centimeter. And secondly, it's double resonant, so it's also resonant for the pump beam. So now we only need 3 milliwatt of power in order to reach a squeezing degree of around 9 dB. And since we don't need that much power, I mean, the frequency doppler light can be used just in a single pass of a waveguide. And the laser we're using is very small. So everything can just be packed into a 17-inch rack, which is what we see here. So this is the type of squeezer we are probably going to use in the future. So you can also think of trying to do this in a real network, try to distribute this through optical fibers. That could be the next potential step. And also, what is maybe even more interesting is try to use local oscillators and not distribute the local oscillator through the network, but using oscillators that are local at the different nodes. Something that we are already now pursuing in terms of quantum key distribution based on continuous variables, where it works actually pretty well. Having a local oscillator at the receiving station, at Bob station, we can generate the secret keys. But of course, there's a big jump from doing this to do this on entanglement or doing this on squeeze state. But this is definitely an interesting next step. Okay, thank you so much for your attention.
I think we have time for one quick question.
Thanks, that was a great talk. To what extent is the state that you use for the distributed sensing optimal, and have you considered using Gaussian GHZ state generalization?
Sorry, second.
Have you considered using GHZ states of CV?
CV or
yeah, Gaussian GHZ states.
Yeah, so I think you will not gain anything. So a CVGSF state. So this is something you produce if using more than one squeezer, right? Yeah. So you have maybe 2 or 3 squeezers, which are then mixed in a certain network. Then you can produce a GSF state. So that means that you're producing correlations not only in between the X quadratures, but also correlation between the P quadratures. But we're only sensing one parameter. So therefore, I think you don't gain anything having correlations in the conjugate quadrature. So I think you will not improve your systems using GSS state. Maybe, but then you probably also have to change your detector.
Let's thank Ulrik again.